Okay, so what did you learn first? Natural numbers. Yes, you learned to count. So like if Olivia came in here and started counting for you, she would say 1, 2, 3, right? All right, what is the next number you think you added to your library? The number 0 came in, so then whole numbers were next. All right, then what?
Integers.
Integers. So then you figured out that negatives were a thing. Okay. All right, so we know whole numbers, we know the 0, we know the negative. What do you think came next?
Rational.
Rational. Good. So our fractions and our decimals came in, and that could also be broken apart into what other category? If it's not rational, it's irrational. Yep. So then your square roots came in, or the decimals. So like because you had certain fractions that the decimals went on forever, right? Like 1/9. That's an irrational number technically. Okay. Where is it down here? Okay, and up until today, these have all been what numbers? Real. Okay, so this is where your number library has stopped. Okay, we get to add more to it today. So if it's not real, what do you think it's going to be? Imaginary is what we're going to bring in. There we go. And our description on the side told you real and imaginary together gives us what kind of numbers? Complex numbers. How'd we do?
A math family tree.
We do okay. It is a math family tree. Yep. We do good? Yeah? All right, so today is all about the number I. I'm so excited. It's one of my favorite things. Okay? So we're going to figure out what is the number I, this thing I've been talking about this whole time. Okay? Then we're going to start to play with it. We're going to add, subtract, multiply, and divide with the number I. All right? Are you excited? I'm excited. Okay. First, here we go. The imaginary unit I, okay? So as we know, not all quadratic equations have real number solutions, okay? For example, if I have x squared equals -3 and try to square root both sides, you would say there's no real solution. Because if you square something, that means it has to be the exact same number, right? 2 times 2, -2 times -2. So whenever you have a positive times positive, or negative times negative, your result is always a positive number, right? There's no way to multiply the exact same two things together right now and get a negative result, okay? So to overcome this problem, some very bored mathematicians created an expanded system of numbers using the imaginary unit I. Okay? I do have a video that explains more about where I came from that I will post on Canvas, and I'll send it to you in Remind. It's not very long, it's like 5 minutes. If you do want more of an explanation, and it also shows how to graph them. We'll never graph in here, but the video just explores a little bit more deeply into it. Okay? So this imaginary unit I is defined as the square root of -1. That is the number I, the square root of -1. Because now if I square that, I get -1. Right? Don't squares and square roots cancel each other out?
Yeah.
So if I square the square root of -1, my result is now just -1. Okay? So I squared now gives me a negative value. And now we can use it to write the square root of any negative number, which is what we're going to do first. Questions so far, Caden? No? We're good? Cool. All right, let's play with it. Here we go. My first one we're going to play with, zoom in over here. I have the square root of -25. All right. So if I were to break this down, I could say that's the same thing as 25 times negative 1. Does that make sense? You can split them up. What is the square root of 25?
Pi.
And now what is the square root of negative 1?
I.
I. So this is 5i. The end.
And we're done with the lesson.
Oh, there's so much more fun that we get to do. Don't cut the fun short.
But it seems so simple.
It is. All right, part B. Part B, we have the square root of negative 72. So first off, how could I separate 72?
36 and -2. I wrote it.
Well, 36, 2, and then negative 1, right? Why did he pick 36 and 2 and not 9 and 8? 36 is the biggest perfect square. Okay? What is the square root of 36? 6. What is the square root of 2? Square root of 2. What is the square root of negative 1? I. So when we put this together, your 6i are outside the radical, your 2 is inside the radical. That's how we write our answers. Okay? If you wanted to do 9 and 8, if 36 and 2 just did not come into your brain, I have that on the board over here next to the calculators. Okay? You would still get there. 9 and 8, the square root of 9 is 3, but 8 can break down again as square root of 4, square root of 2. So square root of 4 is 2, so now you have positive, or you have 3 and 2 outside, gets multiplied to give you that 6. You still get 6i square root of 2.
So just like solve it like you regularly solve.
Absolutely.
And then you just put an I in the middle.
Yep. Yep. That's exactly what we've been doing. All right, over here, I have a number outside the radical. Is negative 5 going to give me an I? Say no. No, because it's not in the square root. Okay? The negative in my square root is where the I comes from. All right, so we break this apart. Negative 5 is just negative 5. But I can split this up as 9 and negative 1. So what is the square root of 9? What is the square root of negative 1? I. So this gives me negative 15i. Like that. Okay. So do we get what I is? And how it's used to help us with square roots of negatives? Okay. Because now we're going to play with it. We're good? Any questions for me? Okay. Here we go. So now that we know what the number I is, we have expanded our number library, okay, to now include complex numbers. Okay? A complex number written in standard form is going to be A plus BI, where A and B are real numbers, and then B has the I attached to it. Okay? The number A by itself is the real part, and then the number BI is our imaginary part. So complex numbers bring the reals and imaginaries together. All right. As long as B is not 0, then A plus BI is going to be an imaginary number, if you were to classify it, okay? Because the I is there, okay? But if A is 0 and you only have the BI by itself, this is special. It's called a pure imaginary number because the real part's not there. Okay. So in the world of complex numbers, A plus BI, if B is 0, which is what you've done up until today, those have all just been real numbers, right? We haven't had I's. If you have both pieces, it's still considered an imaginary number because I is there. And then if A is 0 and you only have a piece with an I, it's considered a pure imaginary number. Cool? So if I have two complex numbers set equal to each other, okay, and we have missing variables like we do down here, okay, to find the values of x and y, we're going to set up those different pieces of a complex number equal to each other. So you're going to do real equals real and then imaginary equals imaginary. So if I have 2x minus 7i equals 10 plus yi, I know they're complex numbers because of the I. Okay? What are my real pieces? 2x and 10. So I can put 2x equal to 10, and guess what x equals? Magic. All right. And what are my imaginary pieces? Negative 7i and yi. Here's my b's. So what is the value of y? Negative 7. And it is just that complicated. Blah, blah, blah. Think you can do part B? That's the sentence I'm trying to say. All right, so you do 5x plus 4i equals 20 plus 2yi. Solve for x and solve for y. And when you get it, check with the neighbor. See if we match. All right, Chloe, how did you set up to find the x?
I did 5x plus 20.
All right, why did you put 5x and 20 together? Because they're both real. Good. And so what did you get for, whoops, what did you get for the value of x? 4. Beautiful. Chloe, pick a friend. Wyatt. Sorry, Wyatt, I should have known better. How did you solve for y? For I was equal to 2yi. Why did you pick those two together? They're not real. They're both the imaginary. And how did you know they were both the imaginary piece? They have the eyes. So what is my value of y? 2. How we do? Too good? Yeah? Yes?
I'm confused because there's a y at 2, so...
Yeah, that's what you're trying to solve for. So you would divide both sides by 2i. I's cancel. 4 divided by 2 gives you that 2. Yep. Yeah, you can think about it as, what could I multiply 2 by to make it equal 4i on the other side? So 2 times 2. We good? Okay, there we go. So weird things are happening. All right, let's start adding and subtracting. So now we're going to get into operations. Okay, we'll add, subtract, we'll multiply, and divide. Okay. What is nice about the number I is it does behave like a variable. Okay, so if we had x in here, you would combine like terms, right? It's the same thought process. Okay, I will behave like x. Okay. Until we multiply. Because if I multiply I times I, we know that's a number, right? We get I squared, which we know is now negative 1. Okay? So that's when it becomes a little bit different. But it does behave like a variable. So when adding and subtracting, like terms are going to be real pieces versus imaginary pieces. Just like what we were doing solving for x and y. So when I add them, I'm going to combine my reals together. So if I have 8 minus I plus 5 plus 4i, what are the real pieces we're going to add together? 8 and 5. 8 plus 5 gives me 13. All right, and my imaginary pieces that we're going to add together are which two pieces? Negative I and 4I. Put those together, what do we get? Positive 3I. There's our answer. Okay. Whenever we add, subtract, multiply, divide complex numbers, your result should always be another complex number. Okay? If you ever have 3 pieces going on, you're not done. You should have a real and an imaginary piece. Okay? My next one is subtracting. What are the real numbers that we're going to subtract together? My real is 7 and 3. What is 7 minus 3? 4. Look at that. All right. And then now I'm going to change colors, please. Thank you. Now we're going to subtract my 2 imaginary pieces. What are they? Negative 6I and negative 6I. So if we subtract a negative, what happens? We actually add. So what's negative 6I plus 6I? 0I. So what is this?
0.
It's 0I, so 4 plus 0I is 4. This is just a real number. How do we feel about adding and subtracting? Good. Sweet. I figured one of each would be plenty. Didn't need to do more. Phones should not be out. Thank you so much. Time to start multiplying. Okay? When we multiply 2 complex numbers, okay, we get to use our FOIL method because it's 2 binomials technically. So we distribute, we do first, outer, inner, and last. Okay, still the method that we're going to use. Remember, when we do the last, those 2 pieces are going to have i's. So when you multiply those together and get I squared, that's going to simplify more. That part won't be done. Okay? You should never have 3 pieces. Okay? You just had ABC, right? AX squared plus BX plus C. That was quadratics because X is a true variable. I is not a variable, I is a number. So we don't leave I squared in my equation. You should still just have a real and an imaginary piece. Okay? We're going to fill this in a minute. Not yet. We're going to come down here. Okay? So multiplying numbers. If I have 4I times negative 6 plus I, what method are we going to use? Not FOIL, but distribution. Yeah, we're just going to distribute our 4I to both pieces. Okay? So what is 4I times negative 6? Negative 24I. All right? What is 4I times I? 4I squared. Now I have 2 pieces, but does I squared ever stay? No, because what is I squared? It is negative 1. So positive 4I squared is the same thing as 4 times negative 1, which is negative 4. So my real number is negative 4. My imaginary number is negative 24I.
Does the real number always have to be in front of the imaginary?
Yes. It says right answer in standard form. So that tells you it has to be real and then imaginary. Good question. Like when we did quadratics, x squared always came first. So same kind of idea. Standard form of real numbers, complex numbers, it goes real and then imaginary. Yep. All right, part B, I have 2 complex numbers. It is time to FOIL. So we're going to multiply first, outer, inner, and last. Okay? It is still distribution. So when I distribute 9 times negative 4, what do we get? Negative 36. All right, my outers, so distribute 9 to 7i. What does that give us? Positive 63i. All right. My inners is where I start to distribute our negative 2i. So what's negative 2i times negative 4? Positive 8i. And then negative 2i times 7i. Negative 14i squared. So I got 4 pieces here. Remember, I should only have 2. Okay. What do you want to simplify first?
The I squared.
You want to do the I squared?
Yeah.
Okay. So negative 14i squared is really what? It's negative 14 times negative 1. So this is really positive 14. Okay. So what is negative 36 plus 14? Negative 22. So that's my real number.
71.
Okay. And then my 2 pieces in the middle get combined. Like if I had 63x and 8x, you would combine them, right? It acts the same. So 63i and 8i give me 71i. There we go. There's my real and imaginary. All done. Okay. One more. I have 5 plus 3i times 5 minus 3i. So let's go through what we just did. 5 times 5. There we go. 5 times negative 3i. 3i times 5. Positive 15i. And 3i times negative 3i. Negative 9i squared. Tell me what you see.
Plus 15I, negative 9, cancel.
Ooh, there we go. Those cancel. That was nice. So what are we left with? 25 plus 9?
Yeah.
And what's 25 plus 9?
34.
34. Okay. So this guy was special, right? My eyes canceled. How did, what made him, oh my gosh, can't talk. What might have given away the very beginning this was going to be a special problem?
There's 5 on both. There's regular 5 on both sides. And then
It's the same thing, but it's just
the I
minus instead of a.
Okay, yeah, y'all both saying the same thing. They have the same real number, but their eyes are opposite signs. Positive, negative I. Okay? That is something special. We're going to come back up here now. Okay? These. So if you have a pair of complex numbers in the form of what we just had, a plus bi and then a minus bi, where b is not 0. Okay? These are called complex conjugates. And you're going to love them, I promise. Okay? Because they come with a little trick. Because they're conjugates, those i's in the middle will always cancel. It will happen every single time. Okay? So you'll always have a real number in the end. So a shortcut we can use is a squared plus b squared. And we always result in a real number. So look at the one we just did. Didn't we end up doing 5 squared plus 3 squared? That's your a squared plus b squared. It's always plus. It's always plus. Okay? Because when you multiply positive and negative, you get negative, but that I squared, which will always be there, always changes it into a positive. So that's a nice little shortcut when it comes to complex conjugates. Okay. And the purpose of those is to help me divide. So they have a purpose. Okay? Since the product of complex conjugates is a real number, we can use these, okay, to write the quotient of two complex numbers in standard form. Okay, so if I have something like 4 plus 3i divided by 2 minus I, we have to fix it. Why would we have to fix this? Why can't I just leave it like it is?
Because I can get canceled out.
Okay, then what do you think?
Is it because I is square root of minus 1, you can't have that in the denominator?
Absolutely, yes. Okay, we can't have I in the denominator because I is a square root. I is an irrational number. We can't have irrational numbers in denominators. Okay, remember how we rationalized the denominator earlier? With like the square root of 2, I think. We multiplied both pieces by square root of 2 to get rid of it. Here, we'll use the conjugate to help us do that same process. Okay, so the y is because, since I equals the square root of -1, we can't have square roots or irrational numbers in our denominator. Okay. Not allowed. Okay. So, if I use the conjugate, my i's go away. That's the purpose. It fixes that problem. And we're left with just our real number. So the quotient I have for us today, I have 4 plus 3i divided by 2 minus I. So I'm going to write this first. 4 plus 3i, there we go, divided by 2 minus I. Okay? So what conjugate do I need to fix the problem? Are we going to do 4 minus 3i, or am I going to use 2 plus I? 2 plus I. The problem is the bottom, right? So that's what I need to fix. So we're going to multiply both pieces by 2 plus I. Okay. Our top will just be a normal FOIL, but our bottom's going to get fixed. Do you want to do top or bottom first? Numerator or denominator? Which one do you want to do first? We're going to do both of them. Numerator? Okay, here we go. So to multiply, get the product, we're going to use FOIL. So I have 4 times 2, which gives us 8. All right, 4 times I, 4i. 3i times 2 is 6i. And then 3i times I. 3i squared. All right. My denominator. I don't have to do the whole FOIL thing, do I? It's a conjugate. I know my i's are going to go away. We can just do a squared plus b squared. So what's my a? 2. What's my b? And don't say I. It's 1. Good. Remember, it's always a plus right there. So positive, negative, your b will always be a positive something. Okay? All right, let's simplify. Which one you want to simplify first? The top? Okay. What can I put together in the top?
The i's.
Which i's? There's lots of i's.
The two middle ones.
The middle ones? Okay. So 4i and 6i gives me what? 10i. I know that's going to be second, right? That's my imaginary part. So what's the real number going to be?
You can switch that to -3.
Okay.
And then you go do 8 minus 3, which equals 5.
Good. So 3i squared is 3 times -1, so that is -3. 8 minus 3 gives me a real number, excuse me, of 5. All right, and what is our denominator? Adding 5. We get 4 plus 1. There's my 5. Okay. Now, I will say most of your quotient problems will stop right here. Okay? But sometimes it will go further, which is why this one is going to, because it does happen to you, so I don't want you to miss out. Okay? how does this one get to go one more step?
Divide by
They can divide everything by 5, right? If my denominator was 4, I couldn't do anything else, I'd be done. Okay? If that 10 was 11, I couldn't do anything else. Okay? All 3 pieces have to be divisible by the same thing. Okay? Again, doesn't happen all the time, but when it does happen, you gotta be able to see it. Okay? So we'll divide each piece by 5, and we get what?
2i.
1 plus 2i. We don't write divide by 1, right? So each of these got divided by 5. How do we feel about adding, subtracting, multiplying, and dividing with complex numbers? You like it? I told you you'd like it. I love it. Uh-huh. I know, everyone's nervous until we do it. And they're like, oh, that's it? I love eyes. Y'all gotta check out my joke on the door when you leave today. Because now you'll laugh at it. You'll see it when you walk out. You also can get my little poster up here now, too.
What's the E?
It's capital sigma, which represents the sum of numbers. So it's the sum. I ate some pie, and it was delicious. All right. I know, you gotta love math humor, right? I got a shirt, too. Not lying. All right, last little piece. You ready? So, again, this book is fantastic about connecting things to the real world. Eyes do exist in the real world, imagine it or not. It's really big in electrical engineering. Okay, so if you're into that kind of stuff, robotics, I believe it comes into play. Anything with electrical circuits. Okay, you might use the J for joule instead, possibly. Okay, but it is used in that field. Okay, so let's look at this. An electrical circuit components such as resistors, inductors, and capacitors all oppose the flow of current. Okay, this opposition is called resistance. Okay, for resistors, and reactance for inductors and capacitors. Each of these quantities is measured in ohms. Okay, and the symbol that is used for ohms is the capital Greek letter omega. All right. So this table over here shows the relationship between a component's resistance or reactance and its contribution to impedance. Okay. A series circuit, that's this little drawing up here, is also shown with the resistance or reactance of each component labeled. The impedance for a series circuit is the sum, so the adding together of the, I can't say this word, impedances for the individual components. Okay, so it wants me to find the impedance of the circuit. So that is this piece right here. Okay, so to find the impedance of my circuit, I need my resistor, I need my inductor with an I, and my capacitor actually gets a negative and an I with it as well. Okay, so to find I have to do R plus Li minus Ci. Sorry for the bad handwriting. Okay, those pieces together is what I'm looking for. Okay.
The capital I, that's just a variable, right?
That's the impedance. Yeah, that's this. Oh gosh, I shouldn't write sitting down. So let's find out what these values are. They're in my picture. Okay, and we have nice little symbols that show me what's what. So what is the 3? Is that a resistor, inductor, or capacitor? 3 is an inductor. That's my L. So the middle is going to be, this is going to be 3I, excuse me. Okay, this is my L. What's my 5 going to be?
Resistor.
That's my resistor. Has a little heartbeat monitor thing going on. What was it? Just 5? Okay. And then my last symbol right here, 4, is going to be our capacitor. Remember, we need negative CI. So instead of just 4, we're going to have negative 4I. It's a hard problem, guys. Can you do it? Maybe. So in the world of our operations, is it adding, subtracting, multiplying, or dividing? Yeah, adding and subtracting. So what is going to be the impedance of this circuit? Almost. 5 minus I ohms. Word problems, word answers, right? If you wanted to draw the Greek letter, that's perfectly fine. That'd be the same thing. Yeah? Cool? How do we feel? About our number I, our new best friend, and he's going to show up to the party all year long. He'll go away for a little bit, and then he'll pop back in, and then he'll go away for a little bit, and he'll come back all year. He's there with
He's a
us.
reoccurring character.
Okay? Huh?
He's a reoccurring character.
He's a reoccurring character, yes.
Can I get an answer, for example, on line?